Welcome to the wonders of physics. Although it looks like I'm dressed as a magician, in fact, what you're going to see tonight is not magic, but rather science. If I were a magician, I might take a magic wand and I might wave it over something and make a fire. But that's not what I'm going to do. If I were a magician, I would have set this trick up by perhaps putting a little explosive cotton on a piece of wire here and ignited it with a foot switch, as I did. So you're not going to see magic, but rather you're going to see science. Now, one of the first things I would like to talk to you about is the science of motion, or the physics of motion. This is one of the earliest branches of physics, how things move. And for the first demonstration, I'll need a volunteer. Who would like to help? Let's see. How about you in the blue shirt? Can you come down here? Right over here. Now, what is your name? Fritz. Fritz? Okay, Fritz is going to help me demonstrate the conservation of energy. Do you ever bowl, Fritz? No. You never bowl, but you know what a bowling ball looks like. You've seen one of these. Yeah. Okay. What we're going to do is demonstrate the conservation of energy using what we call a bowling ball pendulum. Now, Fritz, if you would go and climb on that step ladder over there, and my assistant, Mr. Lovell, will help you. I'm going to attach this bowling ball to a wire. The purpose of this demonstration is to illustrate that there are basically two forms of energy. There's energy associated with something in motion. We call that kinetic energy. There's energy associated with where something is. If I lift this bowling ball up, I give it potential energy. Now, one of the most fundamental principles of all of physics is the conservation of energy, by which we mean that if something has a certain amount of energy, it will always have that amount of energy if you don't do anything to it. So as this bowling ball swings back and forth, energy will continually be converted from potential energy when the ball is up here to kinetic energy when the ball is moving. So Fritz is going to help demonstrate this. Fritz, can you hold that right by your nose? Now just let go of the bowling ball and put your hands down by your side, and whatever you do, don't move. Once more. Thank you, Fritz. You can hop down. Now, there are many ways in which something can move. The pendulum was an example of something that moved more or less in a straight line, back and forth across the room. We can also have something that moves in a circular fashion, so-called rotational motion. Now, this is just a bicycle wheel. I assume you've all seen bicycle wheels, but perhaps not a bicycle wheel that you can hold in your hand and spin around. Now, a spinning object like a bicycle wheel has some interesting properties. First, let me make a pendulum out of this bicycle wheel by just suspending it on this wire from the ceiling, as we did the bowling ball. And you see, nothing terribly interesting happens. It just swings back and forth, just like the bowling ball did. But we can do something else that's interesting. If my assistant, Mr. Lovell, will help here, we're going to put a starter rope, like you might have seen on a lawnmower or an outboard motor on a boat, around this bicycle wheel, so we can get it up to spinning quite fast. This really isn't essential. We could just spin it up with our hand, but it's a little more effective if we get it spinning as fast as we can. And you notice when we do that, the wheel tends to remain vertical, as if it were defying gravity. And this is a property of any object which is spinning. And in fact, that's one reason when you ride a bicycle, you don't fall off. Because as long as the wheel is spinning, it tends to remain upright. Does anyone know what this is called? Gyroscope. Exactly. Now, can you help me here, Tom? He goes through a lot of shirts that way. A new shirt for every lecture. Well, there are many other examples we could show you of motion, but I'd like to move on because I think there are many other interesting things that might amuse you even more. The next subject I would like to talk about is the subject of heat. Now, you might think that heat sounds rather different from motion, and it may appear that there's really no connection between the two. But in fact, there is. In fact, heat is a form of motion. What makes you feel hot is that the molecules in your body and the molecules of the air surrounding your body are moving very rapidly. And the more rapidly the molecules move, the hotter you are. And some of you look a little hot up there. And I hope you don't get uncomfortable. Well, there are many things that we can do that are hot. If we're going to demonstrate heat, I suppose the first thing we should do is make something hot. So I'm going to take a Bunsen burner here. Most of you have probably studied chemistry at some time in your life, and I'm going to light the Bunsen burner to produce some heat. Well, better get a good match, though. Oop. There we go. Okay, now we're making heat. Now this is another experiment that you could do at home if you wish. You have to be careful, however, because it involves heat. Now at home you probably don't have a Bunsen burner, but I suppose you have a stove, right? And you could take a pop can, an orange crush can I'm using, and you'll see why I'm using an orange crush can in a minute. I'll take the orange crush can and I'll put a little water in it, just maybe a half an inch of water. And I'll put it here on the Bunsen burner to warm up. Now, while I'm waiting, can I borrow that scarf? Gee, that's pretty. Can I just use it for a minute for an experiment here? What I'd like to do is just soak this in a little solution here. You don't mind, do you? What is your name? Noreen? Okay. We've got Noreen's scarf nice and wet here. I'll wring it out. And then I'll take some tongs. You don't mind if I just set it on fire here for a minute, do you? This is okay, isn't it? It is burning. Everyone agrees, right? Thank you, Noreen. Hold it up. Is it burned? Let the audience see. Now, how did I manage to do that? Well, I'll explain. A magician would just do this, right, and not tell you how. Magicians are going to hate me, right? You sometimes see magicians do this. The solution that I dipped it in was a solution 50% isopropyl alcohol and 50% water. Now, as you may know, alcohol burns at a fairly low temperature. And so, in fact, the alcohol ignited at a temperature below the kindling point of the cotton that the scarf is made out of. Furthermore, because the alcohol was mixed with water, the water took up some of the heat that was produced by the flame. And so the alcohol basically burned without the scarf catching on fire. So that's a trick you can perhaps do with your friends. It's ordinary isopropyl alcohol that you would, it's like rubbing alcohol that you get in the drugstore. So, it's an example of heat. Who knows at what temperature water boils? 100 degrees. Now, is that Fahrenheit or Celsius? Celsius. Okay, and Fahrenheit, what would it be? 212 degrees Celsius. Very good, except that's wrong. You've probably always thought that, but in fact, water boils at that temperature only at atmospheric pressure, only at sea level. If you go up on a mountain, in fact, if any of you have lived out in Colorado, you may know that it's harder to boil an egg. You have to boil it longer. And that's because water boils at a lower temperature when the atmospheric pressure is lower. Now, I can illustrate that here. In fact, I can actually boil something without heating it up at all. I can take water and I can boil it without heating it. And in fact, behind me here, I have a demonstration which does precisely that. Here I have a vacuum pump connected to a little flask of ordinary, well, it's actually distilled water. And I'm going to evacuate this, and as I do so, you'll see the needle here come down towards zero, indicating that I've taken all the air out above the water. And if you just watch, you will see that as I do that, the water very quickly begins to boil. And it's not hot at all. I can touch it. Now, I want you to just keep watching that for a moment because something even stranger is going to happen, I hope. Sometimes it happens, sometimes it doesn't. As I feel it, it's not getting warm at all, yet it's boiling away. Can you see what happened? Maybe in the back it's hard to see. It froze, turned into ice. What temperature does water freeze at? Who knows? What temperature? 32 Fahrenheit, or 0 degrees Celsius. And in fact, this water, even though it was boiling, began to freeze. And I'll just turn the pump off here because we're done with it now. And I'll let the air back in, as you see here. And it will remain frozen. And as I feel it, it is indeed cold. And it is real ice. So how was I able to boil something and then have it turn into ice? Well, in fact, what happens is that as it boils, heat is leaving the water. Right? When something boils, heat leaves the thing that's boiling. As it does so, it takes heat away from the water, and the water cools off until finally the water freezes. And so you see, with a vacuum, you can not only cause something to boil, but you can also cause it to freeze. Now let's see how our little can is doing here. You see a little bit of something coming out the top indicating that it's boiling, right? Now what I'm going to do is take this can, and I'm going to take some tongs here. I don't know whether you have anything like this at home, but you probably have some kind of tongs in your kitchen that you can pick up something hot with. And if you just boil your can on the stove for a while and pick it up and turn it upside down in some water, look what happens. Now you can see why I used an orange crush can. Oops. So that's one you can do at home, but I should explain what happened. Why did it crush? Well, now think about it. We started with the can with air in it and a little bit of water in the bottom, right? As we began to heat it, what happened to the water? It boiled, and the water turned into what? Steam, right. And the steam then filled the can, pushed the air out. So then after a while, we had a can filled with primarily steam, with maybe a little water in the bottom. And when we turned it upside down in the water, that water being cold caused the steam to rapidly condense. Now when the steam condenses, it changes back into water, and the water takes up much less volume than the steam did. So that left a partial vacuum inside this can. A vacuum strong enough to cause the can to crush. Now you may have thought the water would just get sucked up inside, and it would have, except the steam condensed so rapidly and the hole was sufficiently small that it couldn't go up in here fast enough to keep the can from crushing. So you can do that little demonstration at home and amuse your friends by crushing a can. Now let me show you another demonstration. Is there anyone here that has a birthday today? This works especially well if someone has a birthday. Was yesterday? Okay, what's your name? Kevin? Okay, well I guess that's as close as we're going to come. Kevin had a birthday yesterday. So we're going to do this next experiment in honor of Kevin. And what I'm going to do is light some candles. Kevin, how old were you yesterday? 8? Unfortunately, I only have 5 candles. Well, I have a 6th one. We'll do 6 candles. I wish I had 2 more, but this is all I can do for Kevin. But what I'm going to do is take this candle and bring it over here and light these 5 candles in honor of Kevin's birthday yesterday. 2, 3, 4, and 5. Okay, 5 candles plus a 6th one over here for Kevin. Now I'm going to take something out from behind the table here. What's in here? No, it's not. Well, now watch. Well, now how did I do that? This thing was apparently empty. Does anyone know? Do you know? That's exactly right. This was filled with carbon dioxide, which is a heavy gas, and that's why I could carry it around like this, because it's heavier than the air, and so it sat in here. Now, while we're talking about gases of various sorts, I'd like to show you something with soap bubbles. How many of you have played with soap bubbles? A lot of people. Okay. You know there are certain solutions that you can buy in the toy stores that you can make soap bubbles with. And you may have seen a little pipe that you can put in your mouth and blow bubbles with. I'm not going to do that for you. But rather, what I am going to do is to connect something up here which will blow bubbles. And so I'm going to pour a little bit of this solution, which is just like the stuff you buy in the toy store to blow bubbles, into what amounts to a pipe here. And rather than blowing on it with my mouth, I'm going to turn on the gas here and let it make bubbles. Now this may take a minute before we get good bubbles going. I probably filled it a little too full. Now I want to make some nice bubbles here because I want to do something rather unusual with a candle. Now, have you ever seen a bubble that would do that? First of all, why are those bubbles rising like that? Well, they're rising because they're not air bubbles, but they're bubbles of natural gas. This is connected to the same natural gas that was running the Bunsen burner, the same gas that you would have in your homes, perhaps. And so with bubbles produced with natural gas, first of all, they're lighter than air, so they rise. And secondly, you can ignite them. And it's very pretty. One more. Now, while we're talking about things that are hot and things that are cold, let me show you something that's even colder than dry ice. Anyone know what's in here? Yeah. Nitrogen, exactly. Liquid nitrogen. Now, nitrogen is an interesting substance. In fact, right now you're breathing mostly nitrogen. That's what the air is largely made out of. About 80% of the air is nitrogen. Now, normally nitrogen is a gas at ordinary temperatures. But if you cool it down enough, it becomes a liquid. So here I have some liquid nitrogen. And if I pour it out on the table here, it looks like a liquid, but as soon as it touches the table and warms up, it becomes a gas and just adds to the nitrogen that's in the room. So that's liquid nitrogen, and liquid nitrogen is even colder than that dry ice. Liquid nitrogen is at a temperature of 321 degrees Fahrenheit, below zero. You've probably never encountered in your everyday life, unless you happen to be a scientist, anything this cold. Or stated another way, it's about minus 196 degrees Celsius. Or yet another way, it's about 77 degrees above the absolute zero, the coldest you can possibly be. So this is very cold stuff, and there's a lot of interesting things we can do with liquid nitrogen. And one thing that's always very popular is to take a little cylinder here, inside of which there is a smaller cylinder, and I can lower the cylinder down inside of the liquid nitrogen, and it boils for a while. And after the boiling stops, the cylinder will have come to the very low temperature of the liquid nitrogen. So I'll have a cylinder filled with this very cold stuff. So when I pick it up, I have this little cylinder filled with this liquid nitrogen. Okay? Now what I'm going to do is take that cylinder and lower it down into this larger cylinder, trying not to spill too much. And I'm going to take this cork and I'm going to pound it in. Then I'm going to take the whole thing and I'm going to shake it like this. Now you probably didn't see what happened. Maybe it was too fast. But what happens is that the cork blew off. It went all the way to the back of the room, hit the back of the room, and bounced down here and hit someone. What's your name? Who it hit? Jeff. Jeff. Okay, it came down there and hit Jeff. Didn't hurt you, did it, Jeff? You can keep the cork as a souvenir. Now, why did that happen? It happened because whenever you change a liquid into a gas, the gas occupies a bigger volume than the liquid does. Or stated another way, the pressure increases in order to try to cause it to expand. How many of you have seen a geyser? In Yellowstone Park, they have a lot of these. This is our artificial geyser over here. It's very much the same principle as the real geysers you find out in nature. Namely, at the bottom here, there's a source of heat, a large Bunsen burner, which is heating a column of water. This is filled up to here somewhere with water. And as the water begins to boil, it actually becomes heated above the boiling point at the bottom. But it doesn't boil because the weight of the water keeps it from boiling. It increases the pressure, sort of the opposite of what we did over here. And so it doesn't boil at the ordinary temperature. But once it starts to boil, the pressure is released, and then it boils very vigorously, and the water is sprayed up. And that's exactly the way a geyser works in nature, where there are places in the earth where there are crevices that go deep down into the earth where the rocks are very hot, and water going down into those crevices is heated from below, and periodically they erupt. Now, we've been talking about gases of various sorts, carbon dioxide, nitrogen, natural gas. There's another kind of gas that probably many of you are familiar with because they blow up balloons with it. Who knows what it is? Helium. Very good. Now, I have a tank over here filled with helium, and I have some balloons. And I'm going to fill a balloon with helium just like they might do if you went to the circus or the zoo. You might find someone blowing balloons up just like this, and they tie them off and tie them to a string and give you the string, and you walk around and say, gee, that's really neat. But I'm not going to do that. That's too ordinary. I'm going to do something else with the helium. What I'm going to do with the helium is breathe it. Now, I caution you, don't go home and start trying to breathe things, because most gases that you breathe, even some of the air we breathe, is harmful to you. So there are only a few things you can do this with. Helium happens to be one that you can breathe. And it does a very interesting thing when you breathe it. So watch and listen closely.
And as you see, it has very little effect, except it changes my voice slightly so that I sound like Donald Duck. Now, I'm not just pretending. It's really doing this to my voice. And the reason is that air travels faster in helium than it does, or sorry, sound travels faster in helium than it does in air. And so the natural resonant frequencies of my nasal cavity is increased. And the way you sound has to do with the properties of your vocal cords and the resonant frequencies of your nasal cavity. And so helium alters the way you sound. And you can see as I continue to breathe and the helium is replaced with ordinary air that I begin to sound normal again. Now, probably a lot of you, I'm sorry? Thank you. I will do it again, but the next time not with helium. I'm going to breathe something else. And this is one of the other things that you can safely breathe, and there are not too many of these, but it's something called sulfur hexafluoride. It's in this little tiny bottle over here. And I'll fill up the same balloon with the sulfur hexafluoride. Now, sulfur hexafluoride has the property that, unlike helium, which is a light gas, it's a very heavy gas. And so sound travels slowly in sulfur hexafluoride, whereas in hydrogen, or in helium, it travels rapidly. So it will have somewhat the opposite effect, and I'll breathe it as I did the helium.
And as you see, it has very little effect. It does me very little harm, except it makes my voice rather low. Now, the other interesting thing about breathing sulfur hexafluoride is that because it's a heavy gas, it stays down in my lungs for a long, long time. Unlike the helium, which very quickly rises to the top and out my nose and goes away. So you may have to listen to me sounding like this for the rest of the lecture. But perhaps not. Little by little, I'll begin to sound normal.
But the effect is exactly the same. It's a heavy gas. Sound travels slowly in a heavy gas. It lowers. It always hiccups. Well, that concludes the things I want to say about heat. And I would like to move on to discuss sound. Since I'm talking funny anyway, let's discuss sound. There are a number of things we can do with sound, and they're perhaps best illustrated by turning on an oscilloscope. I may have to come around to the front in order to do this. Watch your feet. I'm going to turn on an oscilloscope. How many of you have seen an oscilloscope? Okay, an oscilloscope is an instrument that displays a waveform of an electrical voltage as time goes on. So you see what this oscilloscope is demonstrating is the waveform of my voice. Now, in addition to this rather ordinary oscilloscope here, we have a different kind of oscilloscope which is displayed on the screen behind me. And I'll just turn off some of the lights here for a moment so you can see that a little better. That's what we call a laser oscilloscope. And this particular device was made by one of our graduate students, John Harlander, who's in the back operating it. So we have, for your amusement, these two oscilloscopes, an ordinary electrical oscilloscope here and a laser oscilloscope. So what I would like to show you now are what these pictures look like for various sounds that we might produce. Now, you're already seeing the sound that's produced by my voice, and you see it's a very complicated picture here. But we can produce sounds which are somewhat simpler. These are things called tuning forks. Now, a tuning fork, you strike with a little mallet, and it makes a sound. And I'll strike these and watch on the two oscilloscopes, and you'll see the sound that these make. Now, let me show you another one. And try to notice the difference between these various sounds. Now, the difference is the higher pitched sound has more wiggles on here, right? It goes up and down more times. And that's what determines the pitch or the frequency of a sound, how many wiggles up and down it has. Now, sound, of course, is a vibration of the air, and so we are converting that vibration of the air into an electrical signal with a microphone that I'm wearing, and that electrical signal is what we're displaying here and on the screen behind me. And I can illustrate that. I have a couple of musical instruments here. I have an old beat-up trumpet. Is there anyone in the audience that by chance plays a trumpet? Anyone here that, I'm not going to ask you to play anything very much, but just could blow a note or two even? Way back there, what is your name? Gabe? Can you get down here? It's a long way to come, but... Now, what I'm going to ask Gabe to do is just blow a note or two here, and I want you to look on the oscilloscope. This one down here is probably a better one to look at, and notice what the pattern looks like compared to those sine waves and square waves that I showed you a minute ago. Now, Gabe, why don't you stand right here, and just, are you very good at this?
Sort of, I know how to play.
What can you play?
Scales.
Okay, play a scale for us. Wait a minute. It's nice and warm in the back of the neck. Go ahead, Gabe. Very good. Thank you, Gabe. Now you notice the sound, the waveform in the oscilloscope was not a sine wave like I showed you here, nor was it a square wave, but it was something considerably more complicated. And in fact, all musical instruments have that property of having a waveform that looks different from every other musical instrument. And if you had experience with this, you could play all different musical instruments. You could look at this picture here. You could tell what musical instrument you were looking at, because each instrument has a different combination of frequencies associated with the notes that it makes. So we could go on and bring out lots of different musical instruments and show you that each one has a different shape, but I won't bore you with that. Well, that brings me to the next topic, which is the topic of electricity. And before I enter electricity, I want to turn off the geyser, because the geyser makes water, and water and electricity don't mix very well, right? So we're done with the geyser, and I would like to show you some demonstrations involving electricity. Now, for the first demonstration, I will need a volunteer. Now, I have to pick just the right kind of person for this. Let's get rid of these. Okay. Who would like to volunteer? How about you? Can you get out of there without tripping? What is your name? Heather? Heather? Wait a minute. Can you stand right up there, Heather? Now put your hand right up there. And are you good at taking instructions? Okay, because it's very important that you do exactly what I say. Okay? So all I want you to do is stand there, and as long as you keep your hand there, everything will be perfectly fine. Okay? And you want to keep your legs back. Now what I'm going to do is turn on this object that Heather is connected to. Heather, can you kind of shake your head now? Shake it. Keep shaking. Keep shaking. Okay. Now stand still, Heather. Don't move yet. See your hair come down? That's when I discharge this dome. Okay, Heather, let me help you down. You can. Thank you. So let me explain what we did to Heather. This is a device called a Van de Graaff generator. The Van de Graaff generator is used for producing very high voltages. This particular Van de Graaff generator will produce about 100,000 volts. And Heather was able to touch the sphere on this Van de Graaff generator only because she was standing on an insulated stool here. And so although Heather was charged up to a very high voltage, she was safe because there was no path for the electric current to travel through her body. And as long as there is no current, there is no danger. So as long as she was on this nice insulated stool, then she was safe and we could charge her up to the high voltage. And as you saw, one effect was that her hair stood on end. And the reason is she had a large electrical charge. When you have an electrical charge, the charges try to get away from each other as much as they can, and so the tips of her hair tried to get as far apart as they could. And so her hair stood up. Now you've all had that experience when you've tried to comb your hair on a dry day when you don't wet it. Your hair stands up. It's exactly the same thing. It's a form of electricity that we call static electricity. Many of you probably noticed the poster advertising this lecture. And in this poster, you saw a picture which didn't reproduce all that well, but it's a picture of someone sitting in a tub of water with a bathing suit on, connected to a large Tesla coil with sparks coming off his head. Now, this is a rather dangerous demonstration, potentially, so I'm not going to ask for a volunteer to do it, but rather I'm going to call on one of my trusted assistants. I'm going to ask Mr. Paul Nahn to come down here. Okay. This could be exciting. We're going to make it look as much like the picture as we can. A little more hair. Now, it turns out to be slightly dangerous to do what you're seeing in this picture for the simple reason that when sparks come off your head, it has a tendency to catch your hair on fire. So in order to avoid, so in order to make Paul as safe as possible, we first wet his head down. That headband we soaked in the water, and we put a little helmet on him, a metal helmet, and the sparks will actually come from the helmet, although the helmet is in good contact with his skin. So the electric currents will actually flow through his body into the helmet and out into the air, much as in the picture that you see here. Now, what good is a human voltmeter if we can't get him to light a light bulb? Can you hold that in one hand? And let's give you something else. How about putting this in your other hand? And we'll turn out the lights and turn on the Tesla coil. Good. Okay, thank you very much, Paul. He's very brave to do that. Now, while Paul is getting out, I'd like to roll forward here another Tesla coil, a somewhat smaller one. That was about a 500,000 volt Tesla coil. This is one that's about 60,000 volts. So when I turn on this Tesla coil, it will make sparks off the top here, much as that one made sparks off the top, but the sparks will be somewhat smaller. So not very impressive, you say, just 2 or 3 inch long sparks. Now you're used to big long sparks, and something like this doesn't impress you very much, right? But there are nevertheless interesting things we can do with a small Tesla coil, and for the next thing I want to do, the small Tesla coil is every bit as big as a big one. Because I want to take one of these balloons. What do you think's in this balloon, by the way? Helium. Now, you think it's helium because it's lighter than air, right? And that's a very good guess, that it would be helium. Now, I want to take this balloon, and I'm going to put it on the end of one of these tubes that we have used before in looking at the Tesla coil, and tie it on. And I'm going to turn on the Tesla coil, and I'm going to bring the balloon over near the Tesla coil. Does anyone want to guess what will happen? Think it'll pop? Well, let's see. Now, first of all, I want you to notice that the tube lights up. So it is indeed a Tesla coil producing voltage, and some of that electric current is flowing through my body now, and I don't feel a thing. It's a very small amount of current. Furthermore, it's a high-frequency current, so it flows on the surface of your skin rather than deep in your body where it can do harm. So let me just pull the balloon over near the spark, and you see what happens. Now, does anyone who thought that the balloon was filled with helium want to change your mind? Because, in fact, the balloon was not filled with helium, but rather it was filled with hydrogen. And hydrogen is an explosive gas. It combines with the oxygen in the air and forms water with a big explosion. And, in fact, that's why balloons are made out of helium rather than hydrogen, in order that such explosions don't occur. Okay. Now I'd like to move on to the next topic, which is the topic of magnetism. Now, magnetism and electricity at first sight perhaps appear to have nothing to do with each other, but in fact they're very closely related. Now, you're all probably familiar with magnets of one sort or another. Here's a couple of what we call horseshoe magnets. They stick together. They're pieces of metal just bent into a shape of a horseshoe. Probably a lot of you maybe haven't even seen horseshoes, but put them on the foot of a horse, and if you put them together like that, they stick, but if you put them together like that, they repel each other. So magnets have north poles and south poles. Now, if you want to make a very strong magnetic field, you don't do it this way, not with permanent magnets, but rather you make magnetic fields with electric currents. And I have a number of demonstrations here to show you how you can use an electric current to produce a magnetic field. Now, here's a device that consists of a big coil of wire. Many, many turns on here underneath this paper. And down through the middle here is some iron, so-called iron core. And what I have in my hand here is a little ring of aluminum. Now, aluminum is not normally a magnetic material. It doesn't stick to the magnet at all. But it is a good electrical conductor. And that's important because what I'm going to do is put this ring on here, and I'm going to plug this in. And I'm going to push the button here, which energizes this coil, and you will see what happens to the ring. It jumps up. You want to see it again? It jumps up off the core. Now you say, well, that's kind of nice, but who cares? What I'm going to do now is make the magnetic field a little more intense. And I do that by adding this big long bar of iron. So what that does is concentrates the magnetic field and extends it up much higher. So now I can put the ring on there, and I can push the switch, and it goes quite a bit higher. Want to see it again? Now, does that amuse you? Higher? Well, in fact, there is a way to do that. I'm glad you asked. I'm going to put the ring in a little dish here, and I'm going to fill the dish with some of this liquid nitrogen that we were talking about a little while ago. Now, of course, as you would suspect, what that will do is cause the ring to become very cold. The ring is very quickly cooling down to the temperature of the liquid nitrogen. Remember that stuff that was 320 degrees below 0 Fahrenheit. And it's boiling. As the liquid nitrogen boils away, the ring is getting colder and colder, and finally the boiling will stop, and that will happen when the ring is at the same temperature as the liquid. And so it's not cooling down anymore. So it's essentially stopped boiling now. And I can take the ring and I can put it on here, and I can do the same thing again. I'll do it once more. Now, why did that happen? That happened because most metals, when you cool them down, they become better electrical conductors. In fact, this aluminum, the conductivity increases about 10 times when you cool it down from what it is at room temperature, when you cool it down to the temperature of liquid nitrogen. So as a result, when I energize this coil, a much larger current is induced in this ring. And so the force of repulsion is much larger when the current is bigger. Now I can show you another example of a magnetic field acting on something which is not normally magnetic. For example, here's an ordinary pop can, an orange crush can, made out of aluminum. So again, it's not at all attracted to a magnet. It's a non-magnetic material. But I can put it in a coil back here, a coil of wire, goes around and around. And behind the table here, where you can't see very well, is a thing called a capacitor. And a capacitor is like a big storage battery. It stores electrical energy. And so I'm going to charge this capacitor up to a voltage of about 8,000 volts. And here on this meter in front of me, you will see it goes up to 10,000 volts when it's all the way up. So I'm going to push the button here, and you'll see the meter come up. That's about 2,000. That's about 4,000 volts. And when it gets up to 8,000, I'm going to energize this magnet. And it's going to make a little bit of a noise, so don't let it scare you. Here's 7,000. Here's 8,000. Said not to let it scare you. Look what it did to the can. Now you can see why I used an orange crush can. The electric current flowing around in the can, induced by the coil that was surrounding it, caused a very intense magnetic field which pushed the can in. And I'll just pass this around. And you can feel it's slightly warm. And it's warm because a very large electric current flowed in it. Now, would you like to see me do it again? No. Everyone except for one fellow in the front row who's going to hold his ears this time, because it's going to make the same sound. Here we come, 6,000, 7,000, 8,000 volts, and we crush another orange crush can. There you go. Now, would you like to see me do it once more? Yes. Except this time I'm going to do something different. Have you ever played baseball? Oh, yeah. You're the star. Because this time rather than put the can all the way down in the coil, I'm going to just rest it on top of the coil. And I'm going to use a 7-Up can. So you can guess what's going to happen. So we're charging up. Here's 3,000 volts. Now again, it's going to make a noise. So be prepared. Here's 7,000. When it gets to 8,000 volts, we're going to release it. Now you can keep the can as a souvenir, but I want my glove back at the end of the lecture. What is your name, by the way? Jim? Okay, thank you very much, Jim. Now, another example of magnetic forces will occur on this apparatus that I have down here. Now, again, we have a couple of coils which carry electric currents. In this case, there are two red coils, one which carries an electric current in the clockwise direction, and the other which carries an electric current in the counterclockwise direction. So that produces a particular kind of magnetic field that is very small in the middle here, but that increases every direction you go away from the middle there. And I can take another one of these aluminum balls. It's like a softball but made out of aluminum, so it's not attracted to a magnet. And I can turn this apparatus on and put the ball in there, and you'll see it stays. It's magnetically levitated. And this is not magic. There's no trick. This is a magnetic field inducing an electric current in the ball, which is causing it to be repelled from the magnets here. Now let me turn it off, and I'll do it again with a different shape object, also a piece of aluminum, but in the shape of a cylinder rather than a sphere. And it's a little more dramatic, but you see it's magnetically levitated. Well, these days people are actually experimenting with trains that operate on this principle, that are magnetically levitated above the ground, so they can move along with very little friction. So you see, magnetic forces can be very large. Now, the reason this works with something that is not magnetic is that this is an alternating current. If you did it with a direct current, this would not work. Because it's an alternating current, it can induce currents in a conducting object which is not normally attracted to a magnet. So, there are many examples we could show of magnetic fields and magnetic forces. But rather, let's move on to talk about the last subject of the evening, and that is the subject of light. Now, light, of course, gives us lots of possibilities of pretty things to look at. And the first thing I'd like to show you is something that's undoubtedly familiar to all of you, and that is an ordinary rainbow. And I'll turn the lights off so you can see it better and let you look for the rainbow. Now, what this illustrates is that white light produced here is actually composed of many different colors, all the colors of the rainbow. And we can separate them with a device here called a prism. And when you see a rainbow out in nature, it's done in a very similar way, except instead of a prism, the light is scattered off of little droplets of rainwater, rather than off of a triangular piece of glass, as I've used here. So a rainbow is a spectacular example of light. Now, there are many other things we could show you. One thing that is very popular is a laser. How many of you have seen a laser before? Okay, now I actually have a laser here. It's contained in this little box, and the power supply for it is right here. And I'm going to turn this laser on, and let's see. And I caution you now, stay in your seats for this, because you see on the wall over there is a spot from the laser. Do you all see that? Way over on the other wall. Now, it's important that you stay in your seats because it's dangerous to look directly into a laser beam. But you can look at the laser beam scattered off the wall, as we're doing now. And you can also look at the laser beam scattered off other things, like chalk dust. Makes a very interesting pattern when we fill the front row here with chalk dust. So watch carefully. Now, normally, you probably assume that light travels in straight lines, right? Have you ever seen light go around a corner, go around a bend? Well, probably some of you have and some haven't, but I'm going to show you that light, in fact, does not always go in a straight line. You can, in fact, make it go around a corner. And I'm going to do that for you if I line things up here very carefully. And I'm going to have to squeeze through here now again. And what I have here is a laser beam shining through this cylinder, which contains water up to about this level right here. Okay, now what I'm going to do is open this spout, and when I do so, water is going to come out of here, and the laser beam is going to shine through the water. And then I'm going to run around and turn the lights out, so watch. So you see, indeed, it is possible. By the way, this looks almost frozen here, but it's not. It's regular water. So you see, it is, in fact, possible for light to go around a bend, as it did in that stream of water. Now I'm going to shine this laser through a piece of plastic here, lucite it's called, or plexiglass. And I'm going to turn the lights off again and let you see what that looks like. Light going around. So you see, light can indeed go around a bend. And it does so in something that we call a light guide. And the water was acting as a light guide, and this piece of plastic was acting as a light guide. And inside of a light guide, what we have is reflection off the surface of the light guide so that the light stays inside. Now, light guides are finding a lot of application these days because you can make light guides out of many little fibers of glass, tiny fibers, and they're called fiber optics. And they're used for example, medical applications where you have to look inside of someone, or anytime you have to look at something that you can't look directly at. You can run these fiber optics into places where you could not ordinarily see. They're also used for communications. Well, that brings me to the end of the presentation this evening, and I would like to conclude with just one last demonstration. You've seen many examples that remind you of meteorological phenomena. We've seen a geyser, rain, we've seen lightning, we've heard things that sound like thunder, we've had explosions, and so forth. So I would like to conclude by showing you, or actually making for you, a cloud. And in order to do that, there's an apparatus here which is filled with liquid nitrogen. I think I can get it. Thank you. Which is filled with liquid nitrogen. This is a big tank of the same stuff that we had in those dewars up there. And what we're going to do is force nitrogen gas into this dewar. That will force the liquid nitrogen up into this cylinder on the top, where there are holes on the top, and then the nitrogen will come out the top and cool the air in the space above the apparatus here. As the air cools, the water in it condenses, and it forms a cloud, just like clouds are produced in nature. So I'll turn this on for you, and that will be the conclusion of the show. And I thank you all for coming.